Am I audible? Okay, let's start. Good evening to all. Welcome to the 10th week tutorial session of NPTEL course, Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. Without wasting much time, we can go into the details. In this week, we will see few problems on carburetor, the week's lectures was basically based on the simple flow type carburetor and its analysis, the mass flow rate of fuel, limitation of simple flow type carburetor. Then a problem, numerical problem was solved on carburetor. Then the engine operating characteristics, mean effective pressure, and the indicator diagram. Then a performance analysis parameters on IC engine, followed by fuels of IC engine and alternative fuel and self-ignition characteristics of fuel, octane number and cetane number. So this week we will see a few numericals and multiple choice questions based on a few of the selected lectures. So we can actually move into the problems. So first problem, a good CI engine fuel should have high octane number, very high cetane number, a short ignition lag, all of the above. Try to think about it. I'll also try to have a discussion after a minute. So did you think about it? So what is the answer? A good CA engine fuel should have high octane number, very high cetane number, a short ignition lag, all of the above. So octane number is a property that we use for SA engine fuels. That is spark ignition for the spark ignition engine fuels. That So these fuels, if they have a higher octane number, that means that they will not have a tendency to knock. A knock is a pre-ignition, that is before the spark reaches the farther corners, it will start to self-ignite. That is called a knocking, and that is not preferable in the case of SA engines, as the it will result in random combustion at farthermost corners, and this will be resulting in knocking. So anti-knock. So if the octane number is high, anti-knocking property is high in SI engines. So that will prevent self-ignition. But our engine under discussion is CA engine, that is compression ignition engine, where the fuel will get automatically ignited. Where the fuel will be injected, high pressure fuel will be injected to the compressed air, and the mixing will be resulting in, and the compression will be resulting in self-ignition. So a higher octane number means that it will be preventing self-ignition. So this is not at all preferred. So option 1 is wrong. Then the second option is very high cetane number. So what do you mean by cetane number? So cetane number is a number just similar to the octane number, but in this case, it is used in the case of CA engines. A fuel with a high cetane number will be having a low ignition delay. That is between the point of injection of the fuel as well as the starting point of the ignition. It will be having a shorter delay. So that is preferable for a CA engine. So this is right. And a short ignition lag, yes. That is a high cetane number ensures that the delay between the ignition point of injection as well as the ignition will be less. So this will ensure sudden combustion. So these two are preferred, option 2 and option 3. Now we can move to the next problem. Look into it. I'll also try to solve within a minute. So choose the correct statement. The first is steady state, steady flow assumption is valid for single cylinder 4-stroke engine due to steady air fuel injection. Second, the same steady state, steady flow is valid for 2-stroke engines. In a simple flow type carburetor, a complete atomization and vaporization of the fuel is achieved. A simple flow type carburetor cannot compensate for the low air densities at higher altitudes. So what do you mean by steady state, steady flow assumption? So in this case, it will be steady state. That is, the properties won't vary with respect to time, like mass, volume, and the temperature. These won't change with respect to time. And in the case of steady flow, the velocity and similar flow and similar parameters won't change with respect to flow. Uh, so these two combined together, the flow parameters, just like the velocity, won't change with respect to time. So this means that all the parameters remains same with respect to the time. So in that case, what we are looking for is that with respect to time, there won't be a change in these parameters as well as the flow parameters as well as the state parameters. Is it valid for a four-stroke engine due to steady air fuel injection? No, because in the case of uh, in the uh, in the case of four-stroke engines, the total the four strokes happens within two cycles. There will be an in stroke where the volume will be the air will be sucked into the cylinder. Then there will be a compression stroke followed by if it is an SI engine, there will be an ignition and then a spark ignition and followed by the power stroke and then the compression for the exhaust of the air. So in this case, uh, there can be possibility of exhaust gas mixing with the exhaust gas mixing with the incoming air and resulting in possibilities of um, temperature and all the parameters changing just like that. So there will not be a steady state just like that for the case of a four-stroke engines. But is it valid for a two-stroke engine? Uh, the same issues that we see in the case of four-stroke can happen in the case of two-stroke engine as well. But here, since the in the case of two-stroke engines, the all the four cycles, all the four things that I have mentioned, that is intake, then the compression followed by ignition powers plus exhaust will be happening in just two-stroke. There will be an exhaust that will happen when the piston expands, and this will be uh, and this exhaust will simultaneously act along with the intake suction. So in the case of a two-stroke engine, when the piston moves upwards, there will be a port through which the exhaust gas will go out, and there will be a port where the fuel has to come inside. When the piston moves upward, there will be the fuel air mixture that will come inside, and just like that, there will be uh, exhaust of the fuel, the combustion fuel. And then when the piston comes back through this narrow corridor, the air fuel mixture will come inside. So note here actually. So the power stroke actually combines with that of uh, the basically the intake stroke. So what happens in this case is two strokes combines coupled together in the case of two-stroke engines. Uh, so so that all the four things can happen simultaneously in two strokes, and that two strokes can be considered as a cycle. So just like the previous case, there can be possibility of mixing, even though mixing between the exhaust gas and the gas which comes inside air fuel mixture that comes inside. But then in the case of two-stroke engine, we can actually consider an average condition or a complete cycle, and this can be considered to be that of a steady state approximation. But even then, it's an approximation, which is not a perfect accurate thing. which is used for a modeling of a two-stroke engines. So there is a lot of processes that are available, like the scavenging, where the incoming air fuel mixture is actually used to push out the exhaust gas. And thereby, if you use an approximate analysis, you can average it out. You can say that average of the components will not vary throughout the cycle in the case of a two-stroke engines. But that is also an approximate analysis, not exactly correct. Then the third one, in a simple flow type carburetor, complete atomization and vaporization of the fuel is achieved. No, that's why this is actually not efficient. That's why we go for better fuel injector or direct ignition kind of things. Then a simple flow type carburetor cannot compensate for the lower air density at higher altitudes. Correct. This carburetor actually uses the. So if you say if the air density is low, uh, the given volume will not be having the given volume that comes inside will not be having sufficient air. So in that case, the velocity will be the same, but the mass component will be less. Based on the velocity, the fuel that we add will not vary, but the actual air component will be less. So in reality, it might become like a rich mixture. And for better combustion, we would be requiring much more leaner mixture for efficient combustion. So and the simple carburetor cannot compensate for that. So electrical or mechanical feedback need to be taken to take into account the incoming air density. So option 2 and option 4 are right. Look into the third problem. It's also a multiple choice question based on IC engine fuels. Sorry, there was a minor power cut. We can actually move into the third problem. With regards to IC engine, which of the following statement is or are correct? Alcohol does not vaporize easily as gasoline. Hydrogen as a fuel in IC engine has detonating tendency. Antinode characteristics of alcohol when compared to gasoline is lower. Hydrogen used as IC engine fuel will have lower aldehyde and carbon monoxide emission. So which out of the following is the right option? Okay, so the options are alcohol does not vaporize as easily as gasoline. Hydrogen as a fuel in IC engine has detonating tendency. Antinode characteristics of alcohol when compared to gasoline is lower. Hydrogen used as IC engine fuel will have lower aldehyde and carbon monoxide emissions. So the first part of the problem, alcohol does not vaporize as easily as gasoline. That is absolutely right. One of the reasons why alcohols, they had tried running alcohol on SA engines, but the reason it's not so that popular is because for the same stoichiometric ratio, we will be requiring twice the volume of alcohol compared to gasoline to give the same power. And it does not vaporize easily. The mixing and vaporization is poor for alcohol compared to gasoline. The second one, hydrogen as a fuel in IC engine has detonating tendency. Yes, it has got pre-ignition tendencies uh, and can result in NOC. Its auto ignition temperature is less. Third, antinode characteristic of alcohol when compared to gasoline is lower is false because it's a poor vaporization. It has got a poor vaporization compared to that of alcohol. Its tendency of NOC will be less. The fourth one, hydrogen used as IC engine fuel will have lower aldehyde and CO emissions. Yes, hydrogen produce water and chances of, since it's not a hydrocarbon, it's purely hydrogen. the tendency of the aldehyde and carbon dioxide formation is less. So the option 1, 3, 1, 2, and 4 are correct. Look into the fourth problem. It's a numerical one based on the four-stroke SA engine. I'll read through and I'll try to solve it now. A four-cylinder, it has got four cylinders and four-stroke SA engine having a bore diameter of 10 centimeter and a stroke length of 9 centimeter runs at 4000 RPM. The fuel used has a carbon content of 84.5% and hydrogen content of remaining 15.5% by weight. The volumetric efficiency of the engine at 75% of full throttle and at 4000 RPM is 0.85 referred to 300 Kelvin and 1 bar. Okay, we are given the volumetric efficiency of the engine at 75% of the full throttle is 85%. The engine is to be supplied with a mixture of air coefficient 0.95 when running at 75% of full throttle. Calculate the throat diameter of the venturi if the air at throat is not to exceed 200 meter per second under the above operating conditions. Also, we need to calculate the rate of fuel in kilogram per second at the pressure drop at the venturi throat. Discharge coefficient for the venturi is 0.8 and the area ratio of the venturi is 0.8. Take R for air as 0.287 and for fuel vapor as 0.09 kilojoule per kilogram Kelvin. It's a straightforward problem. We just need to use kind of an algorithmic approach to get the result. I'll give you a minute to think about, then I'll also try to solve. So we can actually look into the problem. It's a numerical. A four-stroke four-cylinder SA engine having a bore of 10 centimeter and stroke 9 centimeter runs at 4000 RPM. The fuel used has a carbon content of 84.5% and hydrogen content of 15.5% by weight. The volumetric efficiency of the engine at 75% of full throttle at 4000 RPM is 0.85, referred to 300 Kelvin and 1 bar. the engine is to be supplied with a mixture of air coefficient 0.95 while running at running at 75% of full throttle. Calculate the throat diameter of the Venturi if the air velocity at throat is known to exceed 200 meter per second. Also calculate the rate of fuel flow in kilogram per second at the pressure drop at the Venturi throat. Discharge coefficient for the Venturi is 0.8 and the area ratio of Venturi is 0.8. Take R for air as 0.8287 and for fuel vapor as 0.09 kilojoule per kilogram Kelvin. So we can try to solve. First of all, we need to calculate the volume flow rate of the mixture. We are supposed to find the throat diameter and the rate of fuel flow in terms of kilogram per second. These two are the things to find. First of all, we need to calculate the volume flow rate of mixture. So in terms of meter cube per second, it will be written as the volume, the volume divided by time multiplied by the volumetric efficiency. So the actual volumetric efficiency is the actual volume that goes inside is equal to the real volume of the cylinder multiplied by the volumetric efficiency. It's given as 0.85, right? So that is volume divided by time into volumetric efficiency. So this is equal to 5/4 T squared into L divided by T into eta volume. This is equal to 5/4 into diameter is 10 centimeter. So 10 squared into length is 9 multiplied by 10 power minus 6 cube or cube of 10 power minus 2 centimeter to meter conversion. Multiplied by volumetric efficiency is 0.85. What is the time? Instead of time, we can actually write in terms of the revolution per second. So N is given as 4000 RPM. N RPM divided by 60 multiplied the four-stroke four-cylinder engine. So there are 4 cylinders, and the power cycle happens once every 2 RPM. So you have to divide it by 2. So this will give the number of cycles, number of RPM multiplied by the number of cylinders divided by 2 will give you the actual number of cycles where the air will be sucked inside. So if you compare the case of a single cylinder, once every 2 cycles, the air will be sucked inside. It's not once every cycle or once every RPM. So there will be an intake stroke, then there will be compression, expansion for the power stroke, then exhaust. So on these 4 strokes, only 1 stroke is being considered, which will be intaking air. And that happens once every 2 RPM. Once every 2 rotation of the crank. So this just substituting the values 4000 divided by 60 into 4/2. This is equal to 0.08 meter cube per second. So we got the volume flow rate of the mixture. Now what we need to calculate is volume flow rate of the air and the volume flow rate of the fuel separately. What the second part of the problem is the rate of fuel flow in kilogram per second. If we can separate the volume flow rate of the air from it, we can actually calculate, or the mass flow rate of the air from it, we can actually calculate the mass flow rate of the fuel mixture. For that, we need to know the stoichiometric ratio of air to fuel for this particular fuel, and then use it to separate the flow rates. So we can calculate stoichio for a stoichiometric mixture and 1 kg of fuel, air required can be calculated from the mass of carbon as well as mass of hydrogen that is available in the fuel. So 84.5% of carbon and 15.5% of hydrogen is available. So how will we define that? For 1 kg of the fuel, there will be 0.845 percent, 84.5% of carbon, so 0.845. So in this case, if we consider a standard nomenclature, CXH5 corresponds to the hydrocarbon, and then so in this case, what we could see is that X percentage is 0.845 and Y percentage is 0.155. So for every 0.845 carbon, the mass of oxygen in the product will be equal to 32 corresponding to O2, and 0.845 will be the kg, the mass of the carbon. You have to divide by 12. That will be the number of moles multiplied by 2 times oxygen's atomic mass, that is 60. That will be giving us the mass of oxygen that will be present in the carbon dioxide module. And then in the case of H2O, similar to this one, 0.155 divided by 2 will be giving the if 0.155 is the mass of hydrogen, in the reactant side, the oxygen number of moles of oxygen will be half of this one, and the mass of atomic mass of oxygen will be 16. So 16 by 2 into 0.155 gives the oxygen corresponding to this H2O molecule, and these two combined together will give the total oxygen that is in the reactant side. And in order to get a total mass of air, we have to actually use the percentage of the oxygen in the reverse manner. So you have to divide by the percentage of the oxygen by the mass. So air contains 23.3% of the air of oxygen. So basically this one, 0.845 divided by actually 12 into the molecular mass of oxygen, or the atomic mass of 2 times 16 will be giving the mass of contribution from this carbon dioxide. And similarly for this one, the 0.155 divided by the H2, here it will be 1. and then 1/2 because for every two molecule of every two atoms of hydrogen, one atom of oxygen, so 1/2 multiplied by the mass of atomic mass of oxygen divided by 23.3%. This will give you the total mass of air in the mixture needed to stoichiometrically combustion the fuel of 1 kg. So that will be this will be equal to 14.98 kilogram per kg of fuel. But it's mentioned that the engine is to be supplied with a mixture of air coefficient 0.95. So the actual that corresponds to whether this is a lean mixture or a rich mixture. You are actually providing a slightly rich mixture. So actual mass flow rate, actual mass of air based on a rich or lean coefficient equal to 14.98 into 0.95, that is equal to 14.23 kilogram per kg of fuel. Therefore, fuel by air mixture will be equal to 1 by 14.23 equal to 0.07. The total volume flow rate that comes into the cylinder will be a mixture of both of them. So the volume flow rate of air plus volume flow rate of the mixture will be equal to volume flow rate of the air fuel mixture. So we need to calculate the specific volumes of air, specific volume of the fuel at this particular temperature, and from there we can get the mass flow rate of the air. So specific volume R T divided by pressure. So pressure is 1 bar equal to 0.861 meter cube per kg. Ideal gas equation similarly for the fuel. So R is given as 0.09 kilojoule per kilogram Kelvin. So that will be equal to 90 into 300 divided by 10 power 5. That is 0.27 meter cube per kg. Since it's an open mixture, this is an open system. Both the volumes gets added each other. So volume flow rate of air plus volume flow rate of fuel will be equal to volume flow rate of mixture. The mass flow rate of the fuel from this kind of an analysis. How we know the volume flow rate of the mixture, that is equal to 0.08. We have already calculated that. And volume flow rate of air and the fuel will be equal to mass flow rate into the specific volume. The mass flow rate of the air into specific volume of air, mass flow rate of fuel into specific volume of fuel. So the mass flow rate of air will be equal to the mass flow rate of fuel will be equal to 0.07 times mass flow rate of air, or vice versa. Mass flow rate of air will be equal to mass flow rate of fuel divided by 0.07, that will be equal to 14.23. So 14.23 times mass flow rate of the fuel multiplied by new air will be 0.861 plus mass flow rate of the fuel multiplied by the specific volume of the fuel, that is 0.27, will be equal to 0.08. Therefore, mass flow rate of the fuel will be equal to 0.08 divided by 14.23 into 0.86 plus 0.27. Therefore, mass flow rate of fuel will be equal to 0.006 kg per second. So this is from just simplification of this calculation. Now that is the first part. We have to. That's the second part. Actually, we have to calculate the we had actually calculated the mass flow rate of the fuel that comes into the cylinder. So basically, that is the rate of fuel flow at the pressure drop in the Venturi flow. So we had actually calculated the mass flow rate of fuel from the air fuel mixture. Now the first part we had to look the throat diameter of the Venturi if the airflow velocity at the throat is not to exceed 200 meters per second under the above operating conditions. So now we have to calculate the throat diameter. So we know the coefficient of the throat. Sorry, the velocity at the throat. I beg your pardon. The velocity at the throat will be given by the mass flow rate of the air divided by area of the cross section of the throat into rho air, because the fuel doesn't come into picture there. We have already calculated the mass flow rate of the fuel from the previous case. Therefore, mass flow rate of air will be equal to this 0.0039. So this is 639 multiplied by 14.23 air fuel ratio, air fuel ratio. So that will be giving us the mass flow rate of the air. So this will be 0.00639 into 14.23 divided by area of cross section pi by d squared into density of the air. We have to calculate it by P by RT, where P is equal to 10 power 5, R is equal to 287, and this is 300. And there is one more thing that we need to consider here. The area ratio of the Venturi is 0.8, and the discharge coefficient for the Venturi is 0.8. We need to consider the discharge coefficient as well. So that's what I was trying to tell previously. The actual velocity will be equal to c times of the c throat. So then the real velocity, the velocity that we'll be getting should be actually divided by 0.8 to get the real velocity at the throat. So this will be equal to 200, that is given. It's 200 meters per second is equal to is 1.16, the density will be 1.16 into 0.8, therefore diameter will be equal to 2.5 centimeters. So in this problem, we had followed an algorithmic approach. First of all, we had to calculate the rate of the fuel flow. For that, we need to actually determine the actual flow rate of the mixture, AFUL mixture, in terms of volume per second, volume flow rate, and then followed it by the stoichiometric AFUL ratio to get the AFUL ratio, and then a stoichiometric equation to get the AFUL ratio. And from that, we can get the mass flow rate of the fuel, and from mass flow rate of the air and the mass flow rate of the fuel, can calculate the fuel, and using the fuel ratio, we can calculate the mass flow rate of the air. From that, we can get the velocity at the throat using the distance coefficient as well as the other parameters to get the diameter at the throat. Look into the other problem. I'll also try to solve it in a minute. In an SI engine working on the ideal Otto cycle, the compression ratio is 5.5. The pressure and the temperature at the beginning of the compression are 1 bar and 27 degrees Celsius respectively. The peak pressure is 30 bar. Determine the pressure and the temperatures at the salient points, the air standard efficiency, and the mean effective pressure, assuming the ratio of specific heat should be 1.4 for air. So it's a straightforward problem. We need to just draw the PV diagram first to identify which are the state points. It's an SI engine. There will be an compression, reversible adiabatic compression, and then followed by a constant volume. We are actually ignoring the suction part and the exhaust in this one. Reversible adiabatic compression, then there will be constant volume, heat addition process, reversible adiabatic expansion, heat rejection, constant volume heat rejection. So this is the top dead center, and this is the bottom dead center. This can be named as 1, 2, 3, 4 the side. So we need to calculate the salient the points, pressure and temperature, the salient points, and the air standard efficiency and the mean effective pressure. So in this one, we know volume at 2, volume at 3 will be equal to the clearance volume. And also we know the velocity at 0.1, sorry, the volume at 0.1 will be equal to the compression ratio times volume of 2. Compression ratio times volume of 2. That will be equal to RC times VC. So 1 to 2, it's isentropic compression. P2 by P1. Therefore, P2 by P1 will be equal to V1 by V2. PV raised to gamma is a constant, so V1 by V2 raised to gamma, that will be equal to V1 by V2. This is V1 by V2 is equal to 5.5. That is 5.5 raised to 1.4. That is 10.8. Therefore, P2 will be equal to 10.88 into 10 power 5. That will be equal to say 10 point into Newton per meter square. Sorry, it broke code. So I'll write it again quickly. Between process T2 and T1, that will be equal to TV raised to gamma minus 1 is a constant. So using that, R raised to gamma minus 1, that is 5.5, the whole power 0.4, equal to 1.978. Therefore, T2 equal to 1.978 times 300, that is equal to 593.4 Kelvin. Same as 320.4 degrees Celsius. So for the 0.2 temperature, we can calculate using the isentropic compression formulas. Process 2 to 3 is constant volume heat addition. For P3, the peak pressure is given as 30 into 10 power 5 Newton per meter squared. 30 bar. So Therefore, T3 by T2, the constant volume process. Therefore, T3 by T3 is equal to P3 by P2, so 30 by 10.88 and 2.757. Therefore, T3 is equal to 2.757 multiplied by 593.4. That gives T3 equal to 1636 Kelvin, that is equal to 1363 degrees Celsius. So once that is known, we know the points 2 and 3. Now the last point, point 4. For process 3 to 4 is isentropic expansion. So in this case, just like the process 1 to 2, P3 by P4 will be equal to V4 by V3 raised to gamma, which will be same as that of V1 by V2 raised to gamma. That is compression ratio raised to gamma equal to 5.5 raised to 154 is equal to 10.88. Therefore, P4 is equal to P3 divided by 10.88 equal to 2.76 into 10 power 5 Newton per meter square. Therefore, T3 by T4 is equal to R raised to gamma minus 1, that is equal to 5.5 raised to 0.4 equal to 1.978. Therefore, T4 equal to T3 divided by 1.978. Therefore, we have got the temperature at the fourth point as well. So we have calculated the pressure and the temperature at all the salient points 1, 2, 3, and 4. Now the second part we need to calculate the efficiency of the cycle and then mean effective pressure. For an Otto cycle, SA engine as an works on Otto cycle, so the formula will be 1 by R raised to gamma minus 1. It's actually a reduced to 1, a reduced formula taking into consideration constant volume heat addition, constant volume heat rejection, as constant volume heat addition, and the net work output. Compression ratio is given in the problem and gamma is also given in the problem. 1.4 to give the efficiency as 49.43%. Now the last part of the problem, we need to calculate the mean effective pressure. For the indicated mean effective pressure, indicated work per cycle divided by the stroke volume. So this is indicated work is the area of the PV diagram from 1, 2, 3, 4 divided by the stroke volume. Then we have to find the area of the PV diagram. One, two, three, four. That will be equal to the area that is enclosed by this cycle. How to get that? we have to take into consideration. That will be these two are vertical lines. So the area will be equal to the area subtended by this curve minus area subtended by this curve onto the x-axis or the volume axis. So that will be equal to area under 34 minus area under 21. That will be equal to P3 V3 minus P4 V4 divided by gamma minus 1 minus P2 V2 minus P1 V1 divided by gamma minus 1. That is equal to 30 into 10 power 5 into V3. It's actually the clearance volume minus P4 is we have already determined into 5.5 times clearance volume divided by 0.4. Similarly, P2 V2 minus P1 V1 is equal to 10 point. We know the pressures into compression volume V2 and V1 will be 5.5 times compression volume divided by 0.4. So this will give us 23.6 into 10 power 5 into clearance volume. We can actually calculate the value straight away since but for that we need to determine the state points first. We have calculated the pressures, we have calculated the temperatures, but we didn't calculate the volume. We have actually ratio between these two. So somehow if we can, in order to calculate the mean effective pressure, somehow we can represent this VC and VS in terms of the compression ratio. We can actually solve without actually providing the real value. Therefore, the mean effective pressure PM will be equal to 23.6 into 10 power 5 VC divided by VS. So we know the ratio. The VS is a stroke volume, that is VEC this V2 minus V1. So we can represent VC by we can actually get the ratio of VS by VC as that is the compression ratio minus 1. So compression ratio is 5.5. Therefore, this is equal to 4.5. Compression ratio is 5.4, 5.5. This will be equal to gamma minus 1. That will be equal to 4.5. This will be giving us 5.24 bar. That is the mean effective pressure. So this was a straightforward problem for Otto cycle that solves the state points, pressures and temperatures at using the different processes: isentropic compression, isentropic expansion, constant volume heat addition, constant volume heat addition. Since this is an Otto cycle, and then we obtain the efficiency using the standard formula and the mean effective pressure using the theory that is indicated or divided by the stroke volume. Stroke volume to compression, stroke volume to the clearance volume ratio can be obtained from the compression ratio. Look into the sixth problem. It's also a numerical. We actually need to look into the stoichiometric equations and all in this case. So a petrol engine, SI engine with a compression ratio of 7 used a mixture of isooctane and hexane as fuel. The pressure and the temperature at the beginning of compression ratio process is 1 bar, compression process is 1 bar and 55.22 degrees Celsius respectively. If the fuel air mixture is 19.05% rich and the maximum pressure developed is 115.26 bar, then evaluate the composition of the mixture in percentage weight. CV is given as 0.717. Then calorific value of hexane is 43 megajoule per kg, and CV calorific value of isooctane is 42 megajoule per kg. And gamma is 1.31, PV raised to 1.31 is constant for expansion and compression process. So isooctane, its formula C8H18. And hexane formula is C6H14. So 1 mole of C8H18 mixes with X moles of C6H14. That will be the fuel part, plus Y moles of air, that is O2 plus N2 composition. This will give carbon dioxide and H2O plus N2. So writing the stoichiometry equation, XC6H14 plus one mole of C8H18 plus Y times in terms of moles, it is 0.21 O2, not 0.323, plus 0.79 into total will be 1 mole. Gives 8 plus 6 X CO2 plus oxygen. Here it will be balancing the hydrogen. Here it will be 9 plus 7x. That is basically 18 plus 14x divided by 2 to compensate for 2 of the H2 plus 0.79 by N2. Here we equate the number of oxygen atoms on both sides. So that will give us on the left hand side 0.42y will be equal to 2 into 8 plus 6x plus 9 plus 7x. That will give a reduced equation y equal to 1 by 0.42 of 25 plus 19x, that is 1. So this is a stoichiometry case, but the actual air fuel mixture is 19.05% rich. So the fuel air actual mixture is 19.05%, which therefore number of air moles percent will be equal to Y fuel. For corresponding to Y fuel, there will be the stoichiometric case, there will be 1 mole of the for Y air, there will be 1 mole of fuel. but this is slightly richer mixture. So for every y mole of air, there will be 1.19 moles of fuel. So that will be y divided by 1.1905 actual number of moles of air. So that will be equal to the same. Substitute the value of y, that is 1 by 0.42 times 25 plus 19x divided by 1.1905. So this will give us a second equation, 50 plus 38x 2. Therefore, combustion equation can be rewritten as in terms of everything in x times C6 x18 plus C18 x18 plus 50 plus 38x 0.2102 plus 0.79 into. This will give A times CO2 plus B times CO plus 9 plus 7x times H2O plus 0.79 into 50 plus 38x into. Because this is fuel is more and chances of incomplete combustion gives carbon monoxide as well. So now, since we have got a clear understanding, now we equate carbon atoms on both the sides. That will give us A plus B. On the right hand side will be equal to 6x plus 8, right, plus 8. Similarly, equate the oxygen atom. On the right hand side, it will be 2A plus B. Equal to plus 9 plus 7x will be equal to the left hand side. It will be 50 into 0.2, 50 plus 30x into 0.21 divided by 2. So solving for this will be getting it as 8.96x plus 12. B. Therefore, solving A and B, we'll get A equal to 2.96 x plus 4 and B equal to 3.04 x plus 4. So everything we can write in terms of x. Therefore, in this case, we know the state point 2. State point 2, the so 1 to 2 are isentropic compression. So these process follow PV raised to 1.31. This expansion and compression process. So we can actually determine the second point state point pressures as well as temperature based on the equations or reversible adiabatic equations. So state point 2, P2 will be equal to P1 RC raised to gamma, that is 7 raised to 1.31 into P1 1 bar. That's why it will be 12.796 bar. And P2 is equal to T1 RC raised to gamma minus 1 is 328.35 into 7.1.3 equal to 600 Kelvin. So this is the state point 2. Now we have to determine the state point 3. That is the heat addition after constant volume heat addition. It's an SI engine. We know there is +50 38, 50 plus 38x kilomoles of air. Plus 38x kilomoles of air. Then the molecular weight of C6H14 hexane is 86 kg per kilomole, and C8H18 is 114 isooctane is 114 kilojoule per kilogram per kilomole. Therefore, heat added in this process, in the heat addition process from 2 to 3, is just go back and look into the figure of the previous question, PV diagram of the previous question. It follows the same trend. 86x mass into the calorific volume, 43 into 10 cube, that is for every 1 mole of C8H18, C6H14 is there. Therefore, for 1 moles of C8H18 and X moles of C6H14. So this one will be 1 into calorific value, that will be equal to 42 into 10 cube. So this will give us 3698 x plus 4788 into 10 cube kilojoules. Then we have to actually, so we are doing it to determine the temperature at the temperature after the point 3, after the heat is added T3. So we know the heat added, so that will be equal to MCP delta T. So it's a constant volume heat addition to the MCP delta T. So we need to calculate the total weight, that will be equal to 28.97 that is a molecular weight of air multiplied by the number of moles, that is 50 plus 38x plus 86x plus 114 of the fuel. That will give us 1186x plus 1562.5 kilogram. Therefore, this is 3698x plus 4788 88. Balancing the heat added. That will be equal to m dot air plus fuel into Cv into delta T. So this will be equal to Cv. So this will be equal to 3698 x plus 4788 into, actually there is a 10 cube that was missing. M dot is 1186x plus 1562.5 multiplied by given 0.717 into T3 minus T2, T3 minus 600 Kelvin. Therefore, we'll get T3 as a function of x. It's a very slightly complicated one that will be giving us 20 x plus 5460 0.857 x plus 1.12. Now, in the question, we have to actually determine the composition of the mixture. That is, we need to calculate x somehow. So in this case, the maximum pressure developed is given as 115.26. We know the value of T3, we know the value of T2, we know the value of P2 and P3. P3 is given in the problem, P2 we have already calculated. It's a constant volume heat addition process. Therefore, PV equal to nRT you can write, right? So it's a constant volume, so volume remains the same. We can cancel that. For P3 by T2 is equal to T3 into N3 divided by T2 into N1. So initially this will be finally 5.26 divided by 12.796. This will be 4208.66 plus 5460 divided by 0.851 x plus 1.12, and T2 will be 600. This will be equal to N5. That is the final number. N3 in the number of moles after the heat addition. So you have to go back and check how many moles are remaining after the heat addition. On the left hand side, we have got 50 plus 38x plus x of C6H18 and 1 of C8H18. So that will be 51 plus 39x. And on the right hand side, we have got this 0.79 plus into 50 plus 38x, that is okay, into 9 plus 7x of H2 and A and B that you are determined for the carbon monoxide and carbon dioxide. So the right hand side, it will be equal to A plus B plus 9 plus 7x, 9 plus 7x, 0.79 into 50 plus 3.x, 0.79 into 50 plus 38x. And on the left hand side, it will be 51 divided by 39x. Therefore, x, you can calculate the x from this one. So x will become 0.1 after solving this. So that is, therefore, from that we can get percentage of iso-octane equal to 114 divided by 114 plus 86x. That is into 100 percentage into 100 percentage. That will be equal to 93 percentage of iso-octane. Percentage of normal hexane, which is added, which has got a higher calorific value, that will be 7 percentage. So the octane number will actually give the percentage of the iso-octane in the component. If that is higher, then that will be uh, iso-octane and normal hectane. So if the percentage of iso-octane is higher, it will be giving a reduced knocking tendencies. So this was slightly mathematically intensive question, where we have to actually determine the stoichiometric. We have to find the stoichiometric balance, and from that we use the fuels rich mixture and get the combustion equation, actual combustion equation. From there, we will be balancing the moles and then determine the state point 3, and everything will get in terms of the ratio between the number of moles of iso-octane and the normal hexane. And from there, we'll get uh, the temperature of the state point 3 after the heat addition, and one more additional equation, external equation is required to determine the value of x, and that will be provided by the constant that in the problem, that is the maximum pressure developed, that is 115.26. To close the equations, we'll get 93% of iso-octane and 7% of normal hexane. Looking at the seventh problem, the two reference fuels used for cetane rating are has to be cetane. One has to be cetane, not iso-octane, not tetraethyl, not this normal heptane, and iso-octane used for octane number. Tetraethyl lead is not used in case of this one. It's alpha methyl naphthalene and cetane. Higher the cetane number, higher the cetane content. Which of the following statement is correct regarding the petrol engines as well as diesel engines? So compression ratio for petrol engine varies from 6 to 10. That is right. It can't operate at a higher compression ratio. It doesn't work on self-ignition, but it depends on spark ignition. Higher compression ratio in diesel engines result in higher pressures. Yes, that's straightforward. Petrol engines work on auto cycle. Yes, all of the above are correct. Normal heptane content in fuel for SA engines accelerates auto ignition, retards auto ignition, does not affect auto ignition, cannot predict auto ignition characteristics. So in the case of SA engines, octane number is used to characterize the fuel based on their resistance to knock. It comprises of normal heptane and iso-octane. If 100% iso-octane and 0% normal heptane, that will be corresponding to octane number of 100. So this will be having the highest anti-knock tendency. But if the normal heptane content increases, it increases the knocking tendency. That is, it triggers auto ignition, which is not at all preferred for SA engines as it can't take the local ignitions hotspots. Look into this problem. Desirable characteristics of combustion engine for SA engines to avoid knocking should have small bore, short ratio of flame path to bore, absence of hot surface in the end regions of gas, all of the above. The third point is straightforward. It should not be having hot surfaces. Once hot surfaces are there, which is far away from the spark, it will increase auto ignition. Short ratio of the flame path to bore, yes, the flame can easily reach the bore and the diameter ends very quickly. Small bore is straight away adding to it. So the answer is all of the above. So we have completed this week's session, and this week it was based on the problems on carburetors, IC engines, engine operating characteristics, mean appetite pressure indicator diagram, then a few questions on the fuels, alternative fuels, octane number, cetane number as well. So I hope you have understood what I have actually tried to discuss in this week. Next week, we'll see a few numericals and multiple choice based on the same SA and CA engines and the thermal analysis of the IC engines. Thank you.